Okay, let's do this. Taking up the quiz. We'll start with these ones right here. What's the total number of hydrogen atoms in 0.5 moles of NH3? Now you got to note that there are 3 H atoms for every unit of NH3. So you're basically going to times this value by 3. So, and it's saying what's the total number. It's not saying express it in moles. So you're going to have 1.5 mole. Whoops, that's ugly. You're going to have 1.5 moles, aren't you? So 1.5 moles is going to be 6.02 times 10 to the 23 times 1.5, which is going to be about 9 times 10 to the 23 roughly. So C is the answer. Number 2, what's the total number of atoms? And we're going to express this one in moles. In 0.02 moles of C2H6. So in every C2H6, there's 8 atoms. Okay. Again, sloppy writing. Atoms. 8 atoms in every unit. So you're going to have this times 8. So you're going to have 0.16, essentially. B is the correct answer. All right. Question 3. What is the percent mass of oxygen in C2H5OH? So you got to take the total molar mass of C2H5OH, which is around, let me just do this off the cuff, 24 and 6 for 30, and then the oxygen for 16, so that's 46, okay? The oxygen itself is 16, so 16 out of 46, whatever that is as a percentage. Was that 30? Was it 34? Seems about right. And then, which of the following is the empirical formula? Empirical formula, remember, it's the lowest whole number ratio. Lowest whole number ratio. This was actually probably statistically the easiest question. Most people got this one. Should be C4H4SD. This one here I took up on the board in class, but I'll do it again anyways. Right here, which sample has the greatest mass? Okay, mass. We need all these in grams. That's going to be the comparison point. So let's start with this one since it's already in grams. That seems easy enough. 1.7 times 10 to the 2 is 170 grams. Doesn't matter what it is. Turns out it's iron, but who cares? 6.02 times 10 to the 25 molecules of hydrogen. A molecule of hydrogen is H2. So we basically have 6.02 times 10 to the 25 H2s. How much is that? How much is 6.02 times 10 to the 25? Well, 1 mole is 6.02 times 10 to the 23. So we have 6.02 times 10 to the 25. We have 10 to the 2, or 100 moles of this stuff. We have 100 moles of H2. H2 has a molar mass of 2.02 grams per mole, right? So we essentially have 202 grams in A, okay? Because, there we go. Because mass is going to be moles times molar mass. In B, 5 moles of neon. We need to look up neon on the periodic table. Look up neon. 20. Just guesstimate, because it's paper 1, old school paper 1. You don't have a calculator, so you know you got to be able to do it without a calculator. 20 grams per mole times 5 moles. That's around 100, so that's a loser. Loser. It's not going to be enough. Forget it. The other ones are heavier. That one's not heavy enough either. And then 1.2 times 10 to the 24 atoms of silver. That is 2 moles, isn't it? 6.02, yeah. So this is 2 moles, actually, in terms of how many atoms that is. If you're not sure why, you can look down here. 1.02 times 10 to the 24 divided by how much of anything is in a mole, and you're going to get, that's 2s of them. Okay? What's the mass of silver? It's pretty heavy. Around 108. So that times 108 grams per mole. Again, that those moles. It's going to give you around 2, how's my math? Not good. 216 grams. Winner, winner, chicken dinner. Okay, ideal gas question. Temperature in Kelvin of 2, oops, moving it around. 2 cubic decimeters, that's the volume, of an ideal gas is doubled. So we got temperature is doubled, pressure is quadrupled. What's the final volume? So we can forget about that, it doesn't matter. Forget about that, it doesn't matter. Okay, so PV equals nRT. Get rid of those. So we're going to have this ratio to deal with. Okay. Then we can actually sub in a real value for the volume because it said the volume was 2. So let's put a 2 in there. Okay. Then we know that V2, it said temperature is doubled. So we know that T2 is equal to 2 times T1. So let's put that in there. That's 2 times T1. And we know that the pressure is quadrupled. So we know that P2 is equal to 4 times P1. So we can put that in there. 4 times P1. Okay. Then things can cancel here, and we can rearrange to find V2. So you gotta now rearrange this equation to isolate V2. So you're gonna end up with 2P1 to T1 divided by T1 over 4P1. Cancel out what's on top, cancel out what's on the bottom. You end up with V2 is equal to 4 over 4 equal to 1. So the final answer is D. The volume is 1 cubic decimeter. Okay, question 7. What will be the concentration of sulfate ions in moles per cubic decimeter when 0.2 moles of this thing is dissolved in water to give 100 cubic centimeters? So the key is that recognizing that a sulfate ion is this one, SO4 2-, and that there's a multiplier 2 there, okay? That means that for every 0.2 moles of that salt, you're gonna get 2 sulfate ions. So actually you're gonna have a concentration of 0.4 moles of sulfate ions. All right, and then you're putting that into 100 cubic centimeters. We wanna express it in cubic decimeters though, right? So that means we have to change this from 100 cubic centimeters to actually 0.1 cubic decimeter. Okay, so if you have 0.4 for 0.1, you have 4 moles per cubic decimeter. D. Okay, this question here, there are 2 different ways to approach it at least. I'll show you each different way. And then there are even some other ways that I've seen people figure this out, but deduce the mass of SO3 that would contain exactly 1 gram of oxygen. Anytime in my mind they go right from they go right to the masses, I would convert it to percent composition by mass, okay? So I would find that right away. If you say for SO3, what's the percent composition of oxygen by mass? Let's figure that out. So what's the percent oxygen? Well, we know that it's going to be 16 times 3 from the periodic table. That's going to be your O3. And then you're going to divide that by the total molar mass for the whole thing. So that's your, 16 times 3 is 48. So you got 48 plus 32 down here, which gives you roughly, if you multiply that by 100, that gives you roughly 60% oxygen by mass. Okay? So if you know it's 60% oxygen by mass, and you want to know if you're going to get exactly 1 gram of oxygen, you're basically saying 60% of what will give you 1 gram. So I would set up a little like equation like this, where I'm saying let's let x be the total mass. Okay, so then you divide both sides by 0.6. You're going to end up with 1.0 divided by 0.6 is equal to x. If you do 1 divided by 0.6, you're going to end up that x is equal to 1.67 grams. Okay, so that's one way to do it. The other way to do it, and this would probably be a little bit more like classic chemistry way to do it. Mine is a little bit ratio-y and mathy. The other way to do it would be to do a bunch of conversions. Okay, so if we know we have 1 gram of oxygen, right? We can then figure out like how many total moles of oxygen that is. So we could multiply that and say there's, in every mole of oxygen, there's 16 grams of oxygen. Okay, so basically we're taking mass and dividing it by molar mass there, right? We can then convert that to say like, well, how many moles then of SO3 is that, right? If we figure out how many moles of oxygen, how many moles of SO3 is that? Well, it's going to be a third. There's 1 mole of SO3 for every 3 moles of oxygen. Okay, so now our unit went from moles of oxygen to moles of SO3. And then, like, what mass is that of SO3? Well, we know there's 80 grams of SO3 in every mole of SO3. Okay, so again, this is using the molar mass. If we do that, we cancel out moles, and our final result, if you do all that calculation, is going to be 1.67, and our final unit is going to be grams of SO3. Okay, so you could use those conversion factors step by step, or you could solve it like a ratio, like I did up top, using percent mass of oxygen. Okay, this one here was fairly well done, but some people slipped up a little bit. So let's go at it. Compound has the following composition by mass. Okay, there's the various masses. Okay, we're given masses, so to find the empirical formula, remember that's the lowest whole number, like mole ratio, okay, among the constituent atoms or elements. Okay, so we want to get that. So we have to convert to moles. The key is it's a mole ratio. It's not a mass ratio. So for carbon, let's convert them to moles. Use the molar mass and do that. For hydrogen, let's convert it to moles. Use the molar mass. Do that. For oxygen, let's convert to moles. I'm going to use the molar mass of oxygen from the periodic table to do that. Okay? So you calculate all those numbers, and what do you get? Please tell me I have it written on this piece of paper right next to me. No, I don't. Hang on a second. All right. I found a paper here next to me that has it. So basically, and I'm going to round the numbers, but the key is, like, don't round too early. I should maybe just write that here. Like, let's see. Don't round too early. Even though I'm going to show these rounded. But in other words, like, if you keep the huge numbers in your calculator, you have a better chance of having nice whole numbers at the end. Okay? So, all right, when you divide these up, you get, oh God, never mind. The paper I picked did something strange. Yeah, here we go. You get 1.125 for the oxygen. This is moles. You get 13. Let's see here. well, you don't even really get, geez, okay, people are doing strange things in these papers. You don't get that. You get 0.1. Okay. There we go. You get 0.1125 for that one. You get, for the hydrogen, you get 0.135 roughly. And for carbon, you get 0.0567, something like that. Seems about right, I think. Oops. No. There we go. 0.01. Okay, now what you do is, these are all moles, okay? And you use the smallest number there, and that's what you divide everything by. So that's 0.011, right? So you're going to actually divide all these by 0.011. Now, if you're wondering, like, what is the methodology here? Why am I doing this? It's because you know that it's going to make this one a 1, okay? You have to have some reference point. Remember, we're looking for whole numbers. So you got to at least have a 1. If these turn out to be something 2.5 or something, we can multiply them all through by 2. If they turn out to be thirds, we can multiply them through by 3. But we have to basically anchor this to a whole number. This one will end up roughly equaling 12, and this one will end up roughly equaling 5 when you do that. So you know that the empirical formula is C5H12O. Okay, so then part B is if the, I love how I put this on an angle, so cool. Okay, so part B is if the molecular mass of the compound is 176.34. What's the molecular formula? So before we had the empirical formula, C5H12O. But that's not necessarily the same as the molecular formula. It might be some multiple. So the question is, like, what's the multiplier? What's the multiplier? Okay, so we're going to have to take what I would call the empirical mass, and we're going to divide the molecular mass by the empirical mass to get the multiplier, okay? So let's find the empirical mass. The empirical mass is like a theoretical mass, where if the empirical formula was the molecular formula, what would the molar mass be? So it's going to be like 12 times 5 for carbon. It's going to be 1.01 times 12 for hydrogen, and it's going to be 16 for oxygen. You add that up, you get 88.17 grams per mole empirical mass. Take that molecular mass up there, this guy here, 176.34. Divide that by 88.17 to get your multiplier. To get your multiplier, that's going to be 2. That means you got to multiply everything through by 2. All right. So therefore, the molecular formula is C10H24O2. The molecular formula. Okay, and then finally the pressure question. So this one says you get 2 1-liter containers, A and B, that each have 2 grams of gas at 25 degrees Celsius. Calculate the pressure in B. We are going to use PV equals nRT here. Okay, we do not have a single sample of gas. We have 2 samples of gas, and we're being asked to find the pressure in B. Okay, we're not really changing it. It's just they're giving us 4 out of the 5 things, and we have to solve for the 5th. Okay. So we need to solve for pressure. So rearrange it. It's going to be pressure equals nRT over V, right? And then we can lay out each variable. So number of moles. How much number of moles is there? Well, there's 2 grams of it, and the nature of the gas is oxygen. See if I did this calculation already in my own little notes over here. Yeah, so we're going to take mass and divide it by molar mass. We're going to take that 2 grams that they say is there. Oxygen 16 times 2 is 32. So it's going to be 1/16, which as a decimal is 0.0625 moles. Okay, R is the gas constant, R 8.314. We'll use that gas constant if our units of pressure are kPa and if our units of volume are cubic decimeter. So let's make sure all the other units line up. So our volume is 1 cubic decimeter. Love it, straightforward. And then temperature. So the last thing you have to deal with here is make sure you convert the temperature into Kelvin. Remember? So you got 25 plus the 273 you have to add to get it to Kelvin. So that's 298 Kelvin. You plug in all those values. 0.0625 times 8.314 times 298. You're going to divide it by 1, which means you do nothing. And your final pressure is roughly, I think it was 155 or 156 kPa, depending on your rounding. Okay, lastly, it says, without calculation, deduce whether the pressure in A is higher or lower than the pressure in B. Well, the key is here, they said they both have 2 grams, okay? But A is hydrogen gas. This one has 2 grams, but it's the heavier gas, right? So we don't want to do the calculation, but you can think in your mind, you know, how many moles are here? Moles is going to be mass divided by molar mass, right? So this one has pressure, this one has way more moles, okay? And this one's going to have way fewer moles, and that's what impacts pressure. So A will have a higher pressure. A will have the higher pressure. There are more moles of gas in A, basically. And you could go on and say, instead of saying that, you could say A has or hydrogen has a lower molar mass. You could talk about that. Basically, why they're saying don't calculate is they want you to avoid just going like this, going, oh, look, this one is 1, and oh, look, this one is 1/16, and going 1 is greater than 1/16, and that being it, and not having any like written explanation. Okay, they want you to actually process the fact that it's ultimately this number being so small that leads to this number being so big. That's the idea, I guess. Oh, that's an important word. Jeez, I wouldn't even have got the mark. Hopefully this was helpful.